Integration, anti-differentiation, is the reverse of a differentiation. So the rules are all coming from reversing the derivative rule. What kind of derivative rules are there? Product rule, quotient rule, right? Chain rule. And this substitution rule is actually reverse of a chain rule. Okay? Product, what is the product of reversing of the product rule? That is called integration by parts. Now you learn that in Calc 2. And they teach a more complicated version of a substitution rule. And they combine all of them together into something called partial fraction decomposition. That's also integration technique. So you will learn these integration techniques and all sorts of Riemann sum applications. And that's main business in Calc 2. All right. So here it's integration substitution method. First, I'm going to introduce this Leibniz's notation. And this notation kind of easy to learn rather than understand because of Leibniz's brilliance of this notational use. So I want you to look at this one here. This is usually the problem. You are looking at antiderivative f of x with respect to the dx variable, right? What Leibniz is suggesting is that he's asking us to treat as if dx is a number. Dx is not a number. But delta x we've been using in the Riemann sum and the slope of a secant line, that's a number. But you can treat as if dx is a delta x. That's what Leibniz's idea. Then you can see delta x divided by delta u multiplied by delta u is equal to delta x, right? That makes perfect sense. So these two things is kind of justified in terms of delta, not in terms of d, right? Then you look at this dx divided by dy is actually delta x divided by delta y. Can I write this delta u divided by delta x and take the reciprocal? It's the same thing, right? The 2 over 3 is equal to 3 over 2 and take the reciprocal, right? So these terms, it must be the same. And what it accomplishes is that instead of integrating with respect to x, you can integrate it with respect to u, whatever the u is. So it involves your choice in integrating. It's not given. You have to look at this formula in here, decide to make this substitution. U is going to be that chunk right there. Then you calculate derivative of u with respect to x and stick in the reciprocal of that. Then you can change your integral from dx to du. Then if you can rewrite this one entirely in terms of u, you can treat the whole problem in terms of u, if that simplifies. So it is a lot to take. So I'm going to look at example and explain how this one works with example, and hopefully you see it is kind of reverse of a chain rule, and this manipulation it makes sense. If you already know how to do this substitution method using dx and dy, du separated, fine, you can use it. That's a perfectly valid method. Here, what I'm doing is that I skip all the manipulation they usually suggest. All you want to basically computing is this one. So my method is going from here to there straight. Why waste time on manipulating the same thing over and over every time when you calculate? So go straight from there to the bottom line there. So I claim this way you calculate a lot faster. This manipulation makes no sense anyway because it's dx, dy, it's not a number. I will justify this error part separately, just as a statement. Is this justified? We can just prove it. Right now, we're going to focus on examples. So I summarize it here, skipping the old Leibniz's notation. So I'll rather use this version than that. How about override it, because I don't need that anymore. Alright, back to derivative problem. I want you to think about how we are differentiating this function. Now, because you're used to this chain rule, you differentiate it directly, right? Think about how I introduce it. First time when I did this, I first substitute this one with u, right? So that's going to be d dx of u to the 7th, right? And when you differentiate that one, you have 7 times u to the 6th, right? But that wasn't the answer. If this were ddu, then that's the answer. But it's not ddu differentiating u to the 7th. It's a ddx. So I change that to u like that and multiply du dx, right? This is called the chain rule. And you got used to it. You never think about this ever again. You just do it. Formula after formula, you know how to do it, so you don't think about it. But this is how it's introduced. Therefore, what is the du dx? No. What is du dx? This is 7 times u to the 6th, and what are we multiplying here? Du dx, right? No, not u to the 7th. What is u? U is x squared plus 3, right? So what is du dx? 2x. That's how you differentiate, right? So here's a 7 times u back in there, x squared plus 3, the 6th power times 2x. And you know how to go from here to there without doing any of this u thing, right? Now we're reversing it. By looking at this one, I'm expecting you to be able to determine that, if I set this guy u, then I see the derivative. That must be du dx where it's originally come from, right? So we're reversing it. All right, here's a problem that I want to actually use this method to reverse this one. We're computing x times x squared plus 3 raised to 6th power dx. Then right now, we only have one integration technique, substitution rule. We haven't even perfectly introduced this one. Later, you will have integration by parts, more substitution, all sorts of different methods will confuse you. But right now, it's going to be chain rule reversed, right? So you have to make the choice. Okay, what's going to be my u such that I detect it like this. If my u is x squared plus 3, my du dx is right out there, right? Du dx is 2, right? Oh, it's just sitting out there as a multiple factor. You have to detect something like that. So if I set this one equal to u, which is something that you have to discover by looking at this formula, what is my du dx? 2x, right? But is my 2x sitting out there? Not really. X is there, but 2 is missing, right? But it's not too bad. 2x, the missing constant multiple, just like Robert fiddled with 1/3, it's going to be okay. So you go for it. All right? So here's what you do about that problem. First, you make this choice. My u is going to be x squared plus 3. Immediately after that, you compute du dx. What is du dx? 2x, right? Fair enough? All right. So that seems like it's a part of the setup. They ask you to set up u equals something, your choice. And in the formula, it asks you to compute the dy du dx. So that's why I did it, right? That's why I did it. And we're going to use this formula. Leibniz's notation manipulation. All right, I'm going to write it here. X times x squared plus 3 raised to 7th power, right? Dx. And I prepared this one. My choice u is going to be x squared plus 3. And du dx is needed here. So I prepared it. From here is a dx integral, correct? We're integrating this one with respect to x. In the next line, the rule allows you to switch integral from x integral to u integral. You have to pay attention to this one. X integral to the u integral, not this formula. Also pay attention to that. If you use this dx du incorrectly in the test, you will have significant penalty. You have to use dx and du in correct places, right? So from here, the rule allows you to switch to du integral. Then you can't just change dx to du. You got to compensate. What is the compensation? Is this factor you have to throw in to make this dx integral to switch to du integral. All right? This factor you throw in to change the variable from one integral to another is called Jacobian factor. Right? So again, switching from variable x to variable u, you have to throw in Jacobian factor. You can't just switch from dx to u. So let's write that down. I copy x squared and f of x here, right? Make sense? And I change dx to du. You can't just do that unless you throw in Jacobian factor, right? What is the Jacobian factor we have calculated here? Two x, right? Almost 99%. But it's reciprocal, right? 1 over 2x. That's right. Thank you. What is this factor called? Jacobian factor. That's right. All right. Now you're allowed to switch from dx to du, throwing in this Jacobian factor. All you have to now is that change this everything in here in terms of u. Before you actually integrate with respect to u, you got to change everything in terms of u. So what nice thing do you see here? X and x cancels, right? That's one of the motivation or why we chose u equals x squared plus 3. So this 2 cancels, right? How about 1/2? Can I throw that outside? Like that? Fair enough? And you're left with this guy here, right? And this one here is a dx or du now? Dx now? It's a du. You can't just change the x. You have to throw in Jacobian factor. So this is algebra, right? From here to there is algebra. There's no fancy theorem there. So how can you change this one in terms of u? How can I change this inside all in terms of u? Yeah, substitute, right? So you're right. Here from here to, so what do you substitute here? U to the 7th, right? Because u is the whole thing. So u to the 7th. du, right? Now everything is in terms of u. We're integrating with respect to u. So who sees the antiderivative of this one? Right. But you have to increase 1. It's 1/8 to 16, right? So 8th power, right? Plus c in parentheses, but you can throw all the constant outside, right? So is that okay to put like this? Yeah? Yeah. So that's 16. But what's u? X squared plus 3, right? You can throw it back in there. X squared plus 3 raised to 8th power. Plus c, and that's the final answer. I started with 6. That's why it's all messed up. Sorry about that. 6, 6, 6, 6, 7, 7. That's 14. 7 there. Sorry about that. Strange thing happens. So that's the final answer. Right? So you don't believe all that. Realize I'm going to differentiate this one. See if I can get this one back. Now let's do that. If you differentiate this one, constant multiple 1/14 is there, right? This one comes down, correct? X squared plus 3. And this one knocked down to 6 and multiply by derivative inside, right? What is that? 2x. Now 2 and 7 together cancel with the 14. Is that right? Then x times x squared plus 3 raised to 6th power. That's exactly that. So what you got here is just to be verified to be an antiderivative of this one independently. But how do you get here? Leibniz's manipulation called substitution rule. Alright. Here's a summary. You look at the problem, make your own choice of u being something, because you see the derivative of du dx is out there, like 2x and whatever. So you make that choice. Then you can switch from dx to du integral by multiplying the Jacobian factor, right? Jacobian factor. Now you switch to du integral. you have to rewrite everything inside in terms of u before you actually integrate it with respect to u. Then you actually integrate it. Then once the integral is over, you plug back in there u equals hx. And that's what this formula is about. Make sense? I have to go through the example. So you will soon get used to this mechanics, as right now is a lot, but after you do a couple problems, you will soon get used to this one. The key thing is not this mechanical part, is actually you learning what is a good choice of hx. At the beginning, you might go in through several errors and several wrong choices, and hopefully, after you look at many problems, your choice of u is quite efficient. But there are problems out there, it's so tricky, it takes sometimes 30 minutes to make a right choice in a u. That kind of problem, of course, is not going to be in our test, but eventually in Calc 2, you learn that kind of examples. So I'll stop here.